press the bell icon on the YouTube app and never miss another update.
Good morning, students. So far we have completed two chapters or topics, main topics in this unit, that is waves and sound. That is number one, oscillation, and number two, waves, right? Now the important things in waves is the formation of wave, types of waves, right? Now some basic definitions of waves, relation between frequency and wavelength, progressive waves, properties of progressive waves. Now wave equation or equation of a progressive wave, its derivation and different forms, phase difference and path difference, the relation between phase difference and path difference, right? It is very important in understanding the superposition of waves, right? In studying the superposition of waves, we use two things. One, principle of superposition of waves, in which we use phase difference and path difference between two waves arriving at a point. Now intensity of a wave, right? Intensity of a wave, definition, unit and its expression, and what are the factors on which the intensity of a wave depends, right? These things we are discussed in wave, and in our day-to-day life, right, our important sense organs, right? There are sense organs. Important sense organs are eyes and ears. Light waves enables us to see the objects and get information about them. We know that light is a electromagnetic transverse wave. Light is a form of energy that causes sensation of vision. When light from a source incident on a body gets reflected and reach our eye, after reaching our eye, it passes through the eye lens and form an image on the retina of the eye, and now the mind, right, gets the information or sensation of vision through optic nerves. The other important sense organ is ears, E-A-R-S, ears, right? Because here why I am spelling that word is, here we are using two important words, ears and hears, right? So ears are two important sense organs of human body as well as other animals. Now when sound waves produced by some vibrating body incident on diaphragm or eardrum, the eardrum is set into vibration with the frequency of sound, and the mind, right, gets the sensation of hearing, and we will get information about them. So the two important waves in our day-to-day life are light waves, which are electromagnetic transverse waves, and sound waves, right? And generally these waves, when we receive and use these waves, they happens in air, right? Generally for our day-to-day life purposes, they are traveling in air, right? Generally. Now, let us discuss more particularly about the sound in this right chapter. So, we will take let us start with our chapter, that is sound. Right. Now, by definition, right, sound is a form of energy that causes sensation of hearing, right. Sound is a form of energy that causes a sensation of hearing, and we know that energy exists in different forms. Even light is also a form of energy. Sound is also a form of energy. What is the difference? Light causes sensation of vision, whereas sound causes sensation of hearing, right. Now, second thing is, sound is a mechanical wave, right. It requires a material medium for its propagation, right. So now, sound is a mechanical wave because it requires a material medium for its propagation, like a solid, liquid or a gas, and sound cannot travel through vacuum, right. So, in fluids, that means liquid or gas, sound travels in the form of, right, longitudinal waves with a series of alternate compressions and rarefactions. Sound can propagate through solids, liquids and gases. Now, since fluids, that is liquids and gases, can have only a definite volume, a deformation force can change the volume of a fluid, producing alternate compressions and rarefaction, right. Therefore, in fluids, sound is a longitudinal wave. So, when sound is propagating through air, it propagates in the form of alternate compressions and rarefactions. Therefore, sound is a longitudinal wave. However, it is important to note that a solid has definite shape and definite size, that is volume, right. And when sound is propagating through a solid, it may be propagating in the form of a transverse wave, that is possible in, right, solids. But however, the universal medium for air, right, is, although in our day-to-day life, the medium in which we are receiving and propagating wave is air. So, air is considered as a longitudinal wave in general. So, we can conclude the conclusion that hence sound is a mechanical longitudinal wave. So sound is a mechanical longitudinal wave. Right. Now the question is, so how to produce and propagate sound waves? Sound waves can be propagated through any material medium. But how to produce sound? Right? Any vibrating body, right, or a body having mechanical vibrations in a material medium produces sound waves, right? So all vibrating bodies in a material medium, right, produces or generates sound waves, right? Any vibrating body. Suppose if we see the musical instruments like guitar, sitar, etc., when the strings are set into vibration, we can hear the sound, right? When musical instruments are set into vibration, we can hear sound. So whenever we ringing bell of a bicycle, again the vibration produces sound. When we are talking, there are two membranes called vocal cords, right? These vocal cords produce, right, vibration. Its frequency is controlled by muscles and it is transmitted through air, right? So it can reach from the speaker to a listener. Now again, since sound is a wave, it has wave parameters such as amplitude, period, wave frequency, right, wavelength, wave velocity, phase difference, etc. Right. Now here three important things, right, are wavelength, frequency, and velocity. Right. Now regarding frequency, now frequency of sound is equal to frequency of vibrating body producing it. Right. Now the frequency of sound is always equal to the frequency of vibrating body producing in it. Suppose if we vibrate a tuning fork of frequency 200 Hertz, then the sound waves produced have the frequency of right 200 Hertz. That means 200 longitudinal wave pulses pass through a given point in 1 second, right? Right. Now here wavelength and velocity of sound depends on a medium. Wavelength and velocity of sound depends on a medium, right? One thing has to be noted that now sound wave of all frequencies travels with same velocity in a medium. So whatever may be the frequency of sound, sound travels with the same velocity. That means sounds of all frequencies, they travel with the same velocity, right, in a medium. For example, in air at NTP, now speed of sound is approximately 332 meter per second. Sometimes we may use 330 as the standard value, right, but it is approximately equal to 332 meter per second. But in some standard case we can use it as 330 meter per second. Don't get confused, right? Now if we take the frequency of sound is equal to 100 hertz, velocity is same, 332 meter per second at NT. Or if you take 1000 hertz, it is same. Or if you take 30,000 hertz, right, it will be same. Or you take 1 lakh hertz, right, the velocity is same, right? So remember, whatever may be the frequency of sound, right, now sound waves of all frequencies, they travel with the same velocity in a medium. That means to say, sounds of different frequencies have different wavelengths in a medium, right? As we have V is equal to lambda f, or f is equal to V by lambda. Since V is constant, right, if or lambda is equal to V by f, if a frequency is high, wavelength is low. If the frequency is low, wavelength is high, right? Remember that sound waves of different frequencies travel with different wavelengths in a medium. That is very important, right? So now sound waves of different frequencies travel have different wavelengths in a medium. That is important term here, in medium. Suppose in air, when we sound tuning forks of 200 frequency, 500 hertz frequency, 1000 hertz frequency, they all travel with the same velocity, but all the three have different wavelengths. Smaller wavelengths, higher frequency, right? Higher wavelength, smaller frequency, right? Now, the electromagnetic waves range from gamma radiations having very high frequency and low wavelength to radio waves having very low frequency and very high, right, wavelength. But electromagnetic waves of all wavelengths or frequencies cannot be visible, right? Only the wavelength range of 4000 angstrom unit to 8000 angstrom unit approximately are visible to a normal human eye, right? So therefore, the electromagnetic wave of wavelength less than 400 angstrom unit or more than 8000 angstrom unit are invisible to the human eye. Similarly, sound waves of all frequencies cannot be heard by the normal human ear. There is a certain range of frequency, right? Only those frequencies can be heard by the normal human ear. Remember that visible range is measured, visible range of light is measured in wavelength or expressed in wavelength, whereas audible range of sound is expressed in terms of frequency. Because when we take frequency of a visible light, it is very high, of the order of 10 power 14 hertz, but it is convenient to express in wavelength, whereas here it is convenient to express the range of sounds in frequencies, right? So the thing is, sound waves of all frequencies cannot be heard by a normal human ear. Why we are using normal human ear? If a person is deaf, then he cannot hear any frequency at all, right? Now, what are those frequencies which can be heard by normal human ear, and what are those frequencies which cannot be heard by normal human ear? Now, so sound waves of frequencies from 20 hertz to 20,000 hertz are audible or hearable. Audible sound and are called sonics. So the human ear, normal human ear, can hear or detect only those sound waves of a frequency range from 20 hertz to 20,000 hertz, right? Now sound waves of this frequency range is called sonics, or they are also called audible sound, right? Now sounds produced by musical instruments are audible sound. Their frequency usually lies between at 20 to 20,000. In general, their frequencies are around 1000 hertz, right? Now, here. Now, sound waves of frequencies less than 20 hertz are called infrasonics. The sound waves of frequencies less than 20 hertz are called infrasonics. that is 10 hertz, 5 hertz, 15 hertz up to 19 hertz. They are called, right, infrasonics, right. Now, human ear is not sensitive to infrasonics, right, but however, elephants and dogs are sensitive to infrasonics, right. Some kind of special visuals are used, right, in the training of dogs, right. Now, here, sound waves of frequencies, right, more than or greater than 20,000 hertz, or sometimes it can be written as 20 kilohertz. 1 kilo is equal to, right, 1000. So, are called ultrasonics. Right. Sound waves of frequencies greater than 20,000 hertz or 20 kilohertz, right, are called ultrasonics. So, here bats and dolphins are sensitive to, right, ultrasonics, because we know that bats do not have eyes, right. So, they communicate or they get information about the objects around us, right, through ultrasonic waves. The bats, they produce ultrasonic waves of frequencies greater than 20 kilohertz from the reflection, right, refraction and the effects of Doppler effect that we will discuss in later classes, right. So, it will get information about the objects, right. Now, these ultrasonics are also used in radars, that is the, not radars, sorry, microwaves are used in radars. They are used in sonar, that is sound navigation and ranging, right. They are used in, right, sonars, right, to detect underwater bodies like shoals of fish or submarine, etc., right, their position, speed of motion and direction of motion. Again, sonar makes use of Doppler effect, right. We will discuss about sonar, right, when we are discussing about the Doppler effect. Now, that's all about the sound so far, and these are all the basic things we need to understand that one, right. And one more thing is there, you might have heard in day-to-day life, right, in news channels or in papers, because the tension is going on between India and China. There is a warlike situations where you might have heard of supersonic planes, supersonic missiles, hypersonic missiles, etc., right. Now, here the speed of sound in air is about, right, 332 meter per second, or approximately 1200 kilometer per hour. Generally, when we are using SI system, speed or velocity is measured in meter per second, but when practically we are measuring the speed of an automobile vehicle, like car, bus, motorcycle, aeroplane, etc. Right? We use kilometer per hour. 332 meter per second is approximately equal to, right, 1200 kilometer per hour, and here this speed is measured in terms of Mach. 1 Mach speed is equal to 332 meter per second, or nearly equal to 1200 kilometer per hour. Now generally, right, the cargo planes or passenger planes, right, they move with the speed around the 300 to 500 kilometer per hour. But the warplanes, right, Indian warplanes, you might have heard, right, MiG-29, right, Sukhoi 30, Mirage 2000. Now you might have heard that new planes, right, arriving from France, right, Rafale, right, they are moving with very high speed, right, from 2000 kilometer per hour to 3400, right, 4000 kilometer per hour. Around it is 2500 kilometers per hour to 3000 kilometer per hour, and there are planes which we are moving with very high speed, right. Therefore, their speed is generally measured in terms of 1 Mach, 1200 kilometer per hour, 2 Mach, 2400 kilometer per hour, 3 Mach, 3600 kilometers per hour, and we are also having supersonic missiles like BrahMos missiles, Agni missiles, Trishul, Akash, right? They move with the speeds greater than the speed of sound. The speeds which are greater than the speed of sound in air, that is 332 meter per second or 1200 meter per second, are called supersonics, right? So supersonic means it represents speed. All speeds which are greater than 332 meter per second or 1200 meter per second, right, that is speed of sound in air at NTP, are called, right, supersonics, right. Now speeds greater than 332 meter per second or 1200 kilometer per hour are called supersonics. A supersonic plane means it can move with a speed greater than 1200 kilometer per hour, right. Now these are all some basic concepts which we use in the study of sounds, and we need to understand, right, these properties of sound, right, and what exactly is the sound. So far we have discussed some general concepts regarding that one. Now as far as our syllabus is concerned, right, we have properties of sound. Right. Now we will discuss some properties of sounds. Some properties which we have discussed, right, in introduction topic. So far what we have discussed is introduction to sound, right. Now we are taking the property of sound, right. So number one, sound is a form of energy that causes sensation of hearing. So number 2, sound is a mechanical wave or non-electromagnetic wave or elastic wave, because it requires a material medium for its propagation, right? So sound is a longitudinal wave in fluids, that is, right, liquids and gases. But sound may be transverse wave in solids. In solids, there is a possibility of longitudinal sound wave and transverse sound waves. That depends upon how the configuration of the solid changes. If the configuration of solid changes only in shape, then the sound produced in the form of transverse waves. If the configuration change is only due to change in volume, then sound propagates in the form of longitudinal waves. So both are possible, but in liquids and gases, right, only possibility is, right, longitudinal waves. Now, fourth one, sound travels with a constant speed or velocity in a material medium. In a material medium, provided temperature is constant. So, sound waves of all frequencies we can take. They travel with the same velocity or speed in a material medium provided temperature is constant, right? Suppose we say that when we say speed of sound in air is 332 meter, we have taken at NTP, that is at normal temperature and pressure. The temperature is 273 Kelvin or 0 degree Celsius, right? Even in air, right, velocity of sound is different at different temperature, right? Now, fifth one, velocity of sound is different in different material medium, right? Velocity of sound is different in different material medium because sound is a mechanical progressive wave. Its speed in a medium depends upon two properties: elastic property, that is elastic constants, and density of the medium, right? Since different materials have different values of elastic constants and different density, obviously speed of sound is more, right? Now this velocity of sound in solid is greater than velocity of sound in liquid is greater than velocity of sound in gas. For example, at ordinary conditions, velocity of sound in air is 332 meter per second. In water, it is about 1400 meter per second. In solid copper, it is about 3000 meter per second. Again, in different solids, speed is different. In different liquids, speed is different. And different gases, right? So, among the gases, speed of sound is the highest in hydrogen. And it is different in different gases like helium, nitrogen, oxygen, etc. Right, at the same temperature, velocity of sound is different in different gases like air, hydrogen, oxygen, nitrogen, helium, etc. Is that clear? Now the sixth property, right? So we know that velocity of sound or speed of sound, whenever we are not considering the direction, we call it as speed, right? Now when sound travels from one medium to another medium, its frequency remains the same, because frequency of sound is equal to the frequency of vibrating body producing in it. A tuning fork of frequency 200 Hz is set into vibration either in air or in water or in any other material medium. Frequency remains same, but velocity changes when it travels from one medium to another medium. Why velocity changes? Because we know that V is equal to lambda into F, right? Since frequency remains the same, wavelength changes, consequently velocity also changes, right? When sound travels from one material medium to another material medium, its frequency remains same. Why? Because frequency depends upon vibrating body, but wavelength and velocity are different, change, because both wavelength and velocity, they depend upon elastic property and density of the medium, right? So here, when sound travels from one material medium to another material medium, its frequency F remains the same, but wavelength lambda and hence velocity or speed change. So why velocity changes when sound travels from one medium to another medium? It is because of the fact that though frequency remains changed, wavelength changes. As wavelength changes, consequently velocity also changes. Now another property, seventh one, sound undergoes refraction and total internal reflection. Right. So sound waves exhibit or undergo the phenomenon such as reflection, refraction and total internal reflection. Right. So reflection is the phenomenon when a wave incident on some surface, right, gets right bounce back to the same medium. When light incident on a mirror, it gets reflected back. Similarly, echoes are due to reflection of sound from huge surfaces at certain distances. Now, when light right undergoes refraction, it travels from one medium to another medium. When a torchlight is focused on a glass, light travels from air to glass, and when light travels from air to glass, its velocity changes. The change in velocity of light when it travels from one optical medium to another optical medium is called right refraction of light. Similarly, when sound travels from one material medium to another material medium, its velocity changes, and this phenomenon is called as refraction of sound. And total internal reflection. So when a wave travels from one medium of different densities to another, right? It may, instead of refraction, it may get reflected back to the same medium, right? And this phenomenon is called total internal reflection. We will discuss this total internal reflection when we are discussing about the phenomenon of reflection, refraction and total internal reflection, that is in the case of geometrical optics, right? Now, property number 8. Now, sound exhibits interference and diffraction. Now, all types of waves, electromagnetic, mechanical, longitudinal, transverse waves exhibit both interference and diffraction. The formation of beats, a kind of music, is due to the interference of sound. That means overlapping or superposition of two sound waves of slightly different frequencies. Now, the diffraction of a wave means it is the bending of a wave around the corner of an obstacle. Suppose you are sitting in a classroom and a student is speaking in another classroom. You can able to hear the sound, but you cannot able to see him, because sound produced by him bends around the corners of the window and doors and reaches you, but light cannot diffract around the corners of doors and windows. That we will explain again while discussing about wave optics or physical optics, right? Now, the ninth one, sound waves do not exhibit polarization, whereas light exhibits polarization, right? Sound does not exhibit polarization. It is because of the fact that only transverse wave can exhibit polarization and longitudinal waves do not exhibit polarization, right? Sound waves being longitudinal waves, they do not exhibit, right, the phenomenon of polarization. Now the 10th one, when sound incident on a surface, it sets the surface into vibration. Suppose when sound propagating through a material medium incident on a surface, solid surface, say surface of glass, it sets the glass surface into vibration. Sometimes you might have observed that whenever a heavy vehicle like a heavy tractor or moving through our road, sometimes the window panes, glass panes of windows, right, produce sound, right. We observe that they begin to vibrate, right. That is one of the important property of sound, because whenever I am speaking to a listener, the sound waves of certain frequency, they incidents on the diaphragm of the ear. Now the diaphragm of the ear began to vibrate with the same frequency of sound, and that sends information to the mind, and mind has the sensation of hearing, right. Now this is one of the important thing. When sound incident on a surface, it sets the surface into vibration, and obviously the frequency of vibration of the surface is same as the frequency of vibration of incident sound. If the difference between natural frequency of the surface and frequency of incident sound is very large, the amplitude of vibration is very small, so that we can hardly observe the vibration. But when natural frequency of the surface is equal to the frequency of incident sound, then the surface vibrates with maximum amplitude and the surface may break, right. You might have observed that whenever explosions are happening at certain distances, 1 kilometer away, 2 kilometer away, but in our region the window panes of the glass can break. This is due to the same property. When surface vibrating with maximum amplitude, then the phenomenon becomes, right, the resonance phenomenon, right. Right. Now, so far we have discussed about some basic concepts regarding sound as well as properties of sound, right. Now, try to understand the concept what we have discussed today, right, and right, try to remember all those things which will help us in understanding the sound in a better way. And in the next class, let us discuss speed of sound in a gas. Two important formulae regarding speed of light in gas. One is Newton's formulae and Newton Laplace formulae, right. So, in the next class, let us continue with the concept of speed of sound. Until then, thank you very much and have good time.